This week we're learning about radiation and where our energy comes from for the atmosphere. So we're going to be dealing with both solar radiation, which brings in the energy, and terrestrial radiation, which sends out some energy. So, so how does the energy flow in and out of this atmosphere to maintain a stable and habitable planet? There's two key words at the end. It's stable and it's habitable. Uh, In other words, the energy flow isn't tremendously changing over time. So, what is electromagnetic radiation? It's like radio waves, or if you got X rays, uh, or we've all heard probably about the radiation caused by nuclear explosions or like your fission or fusion. All of that is a different form of electromagnetic radiation. Visible light, what you see, is a part of electromagnetic radiation. And it sits right in here in where the visible light spectrum is. Really not a lot of range compared to how far the different wavelengths can be. And what is a wavelength? Maybe we'll start with that. Well, think about it. These are waves. So in other words, like with anything, they have a peak and a crest, and bottom out, downward. So from one crest to another crest is a wavelength. If you are out in the ocean, when you have a wave hit you, if the wave hits, it's a high point, the water goes down, then it comes back up and another wave hits. The length between those two points, the high points, is the wavelength. Now, electromagnetic radiation is different than a wave in the sense that it runs at the speed of light. So it doesn't matter whether the wavelength is extremely short or fairly long, it's still moving at the speed of light. And we kind of classify these waves, electromagnetic radiation, by their uses. In other words, there's radio waves, uh, FM radio, AM radio. There's microwave radiation, which is used in our weather radars or other kind of radars out in the world. Microwave ovens, ultraviolet radiation, beyond violet, relatively shortwave radiation. A lot of the sun's radiation is in that range. So is visible radiation. And then finally, infrared radiation. That's what the Earth emits. So a black body, for all intensive purposes, absorbs all the radiation it receives and reemits it all right back out. So it's a perfect absorber and perfect emitter. When we kind of approximate Earth and Sun as that, they're not, but they're close enough that we can simplify a lot of radiation physics if we do that. In other words, one part of this is Wend's displacement law. In other words, most intense radiation emitted by a black body is inversely proportional to its absolute temperature. So the wavelength of the sun, very extreme absolute temperature, going to have very, very tiny wavelength. Wavelengths, on the other hand, of the Earth's temperature runs much more, much cooler than the sun. So that's going to give you a different wavelength. And here you can see visible light, ultraviolet, and infrared. Infrared, it would be the Earth. Visible, a lot of the sun's radiation. Ultraviolet, again, some of the sun. So, interestingly, the amount of energy a black body emits is proportional to how high the temperature is or how low the temperature is. So, in other words, if the temperature is extremely cold, we're not getting a whole lot of radiation out of it. If the temperature is extremely hot, like the sun, we're getting a tremendous amount of radiation. And actually, you can see here, this is data collected from a satellite on how much radiation is coming into the Earth. And interestingly, it corresponds pretty doggone well to how much we should get if we had the sun's radiation. Another interesting thing is that for every distance you go out from the sun, we use the Earth as being exactly 1 astronomical unit. If you go 2 astronomical units out, it would be 1/4 the power. In other words, if you go out 2 astronomical units from the sun, like Mars is almost 1 1/4 or 1 1/2, that's how much less energy is reaching it. If you go 3, it's 1/9. If you go 4, it's 1/16. It goes down very quickly. So the further away you go from the sun, very quickly the amount of energy you're receiving from it diminishes. So how do we get this energy from the sun? Well, just a real quick thing. It's fusion. So what it does is 4 hydrogen atoms join together, fuse to make 1 helium. And believe it or not, there's a little tiny bit of excess mass. Well, guess what? Energy equals mass times the speed of light squared, which the speed of light is pretty doggone fast. So that means that just a tiny amount of mass being extra creates a tremendous amount of energy. Different parts of the sun are this photosphere, which is the visible surface, a little cooler than the interior. Sunspots are cool relative to around them, and changes in sunspots can actually affect Earth's climate to a point. And the outermost sphere of gases around the chromosphere is actually the hottest part of the sun. So now that we've talked a little bit about the sun, we know it releases the most radiation to the Earth. It drives the atmosphere. All right, let's look at how it hits the Earth. So if I live at the equator, and today is an equinox, so September 21st, March 22nd or 21st, the sun is going to be directly overhead at noon. I mean directly overhead. If you were looking straight up, you'd be looking straight at the sun. There'd be no angle. You'll notice that is a tiny circle. Pretty powerful. All the energy from the sun concentrated over that circle. Now, if I go 20 or 30 degrees north or south, that angle changes. The sun is coming in at a different angle. It's not directly overhead. That means that same energy that's covering that little small area at the equator is now covering a much larger area. So that any point in that area is not receiving as much energy as if you were directly over the sun, directly overhead at the equator. That is why the further north or the further south you go away from the equator, the less radiation you receive, the less energy you get. So it's colder both directions somewhat. And here you can actually see it. We talk about the solar altitude as being 90 degrees. All we're saying is, okay, here's the sun coming in. The angle from the Earth to where the direction of the sun is 90 degrees. If I, at that time of year, I live at 38, almost 39 degrees north. My angle at that moment in time, I'll say it's 39 degrees. If I were at the North Pole at that moment in time, it's 0. So basically just barely nicking it. All right, the atmosphere is not completely transparent to solar radiation. So the more atmosphere the sun has to go through, the less energy it's going to get there. So as it passes through at low angles of incidence, like 0, it's going to go through a lot of atmosphere, and it's not going to give as much radiation. More radiation, more energy will come when the sun is more directly overhead. And here you can see that change. Here's Antarctica. Notice in their winter, which is the opposite of ours, no radiation. However, notice in their summer, because they have a very long day, matter of fact, they have 24 hours of daylight, they get significantly more radiation. Now, if you're down around the equator, it doesn't vary a whole lot throughout the year. Rockport, New York, not far from where our latitude. You can see how it goes down in winter, goes back up in summer. Actually peaks higher than the equators in summer. It just doesn't stay as long as the equator does. You can see this as the sun is in the center and the earth is rotating around it. So as the earth rotates, here's the sun. In the wintertime, it's tilted. The southern hemisphere is tilted more towards the equator, towards the sun. So it is receiving more direct sunlight. In the summertime, our part of the earth is tilted more towards the sun. We're receiving more direct sunlight. And here you can see how the angle, literally you can see an angle of where the sun is hitting the earth. And here's the other opposite angle as well. So the Earth's motion and space all dictate how long the days are as well. In other words, around the equator, the day doesn't change a whole lot. But interestingly, on equinoxes, everybody in the whole Earth, day is 12 hours. Now, as you go into our wintertime, you'll notice the amount of sunshine, winter solstice, days keep getting less. And if you're way up north, even much less. Summertime, we get longer days. And if you're way up north, they get way longer days. So that it also helps to influence how much solar radiation reaching these areas. So as the solar radiation is coming through the atmosphere, it's impacted by how much is absorbed actually by the atmosphere itself, how much is reflected, which is a form of albedo, and how much is transmitted to the Earth's surface. All of that has got to equal 100% of that total radiation coming into the Earth at that point. So scattering is a kind of form of reflection where the energy just goes in all directions equally. Here you can see it on top of clouds. Albedo. Uh, my favorite example of that is in the wintertime when it's been bright, big, fresh snow. You walk outside, sun's out bright. You need sunglasses because you can hardly see. If you're going skiing and there's bright sunshine on a fresh snowpack, that is a very high albedo. It's reflecting tremendous amounts of the sun's radiation. One of the reasons why it can't get very warm when you have a lot of snow cover. Absorption. Well, up in the upper atmosphere, particularly the stratosphere, we get a lot of chemical reactions, and they're all based on ozone. What they do is prevent much of the ultraviolet radiation from reaching the Earth, significantly reducing it. So the better that chemical reactions are doing their job, it keeps the Earth habitable. The less ozone, the more ultraviolet radiation reaches the Earth, the better chance you're going to get skin cancer, the better chance you're going to get other illnesses from. Our body is not designed to like ultraviolet radiation. And you can see here how it's changed since the late 70s and all. Here's actual chemicals that they show have made a difference. The ozone layer, the CFCs and halons and all that. And they stay there for years at a time, decades and centuries even really, so that it takes a long time to make the atmosphere clear up from these kind of things. And the reason they only form down in the Antarctic atmosphere mainly, there's a slight one in the Arctic, but the Arctic is a little bit warmer. It takes extreme temperatures to cause these reactions. Albedo. Interestingly, here you can see the different albedos. Old snow, fresh snow, 95% of the sun's light is reflected. Now, if you have water, only 3 to 10%, so it's not much at all. So here is the tables of actually how it works. The Earth's atmosphere reflects 30% of the energy it gets from the sun. It absorbs another 23, and the rest is absorbed by the Earth. And because of that higher absorption by the Earth, the air near the Earth's surfaces is warmer and then cools the further up because it gets less and less heat. All right, why do we care about the greenhouse effect? We said Earth emits infrared radiation. Well, there are certain gases that have no influence whatsoever on absorbing ultraviolet or sun radiation. However, they do absorb infrared radiation and they re-emit that radiation in both outward and back towards Earth. These are called the greenhouse gases. And it's a good thing we have some. If we didn't have them, the temperature would be too cold, actually about almost 20 degrees colder to 30 degrees colder than it is now. So we want those. We just don't want too much of a good thing. So when you have a greenhouse gas, the atmosphere absorbs the infrared radiation and sends it back, keeps the Earth warmer. So it's kind of like a greenhouse in effect, where it would let in the ultraviolet, but it doesn't let out the infrared. What is the biggest greenhouse gas? It's water vapor. And interestingly, the hotter the atmosphere is, the more water vapor it can obtain. So the hotter the atmosphere keeps getting, the more you add a greenhouse gas in water vapor, so it keeps getting hotter. Carbon dioxide is the next most. So if I wanted to argue on how this works, classic example is Gulf Coast versus the desert Southwest, or any desert for that matter. In the desert, there's very little water vapor. So during the day, if they're both at the same latitude, they see the same amount of radiation. That radiation comes in, temperatures rise. Afternoon, evening, now there's no infrared, no ultraviolet radiation coming in. So the Earth is re-emitting that infrared radiation back out into space. If I have a lot of greenhouse gases, we'll say water vapor, in the Gulf of Mexico, around that area, that greenhouse gas is absorbing that infrared radiation and emitting it back down, keeping the Earth warmer. However, from in the desert, I don't have that. So therefore, the desert gets much cooler at night compared to where the water vapor is much higher. A man by the name of Callender started studying carbon dioxide a number of years ago. And interestingly, carbon dioxide goes up and down during a given year. Why is that? Well, photosynthesis uses up carbon dioxide. So in the northern hemisphere, where more land is, when the plants are out, photosynthesis is using more carbon dioxide and lowers the amount of carbon dioxide in the atmosphere. Then in the winter, plants are going dormant. There's less carbon dioxide being used. It goes up. That's why it's a spiked curve here. But notice how it's been going up steadily. You draw it. Ever since the 1960s. So there's more and more carbon dioxide every year in the atmosphere and an increasing rate of it. What scientists have proposed, and they've done research looking at satellite data as how the atmosphere is responding. And they've even looked at years when industrial plants and stuff didn't do so much, like during COVID. And they found that really contributes significantly to the amount of carbon dioxide in the atmosphere. Yes, there are other factors, but the current concentration is about 40% higher, and it's actually the highest in the last 800,000 years. So, with that in mind, temperatures are going up, and they have been steadily, and they're increasing, you know, at a rate maybe that's going to exceed about 1.5 degrees Celsius between 2030 and 2050. Ah, that's still on the relatively low end. I've seen some that are a lot worse. Remember, Celsius, that means an increase of like 3 degrees Fahrenheit. So if you took at the average temperatures in the United States, we would change West Virginia's climate from where it is to be much closer to northern Alabama. And in some ways, that's not a bad thing. In some ways, that's not a good thing. It would allow different species of animals to propagate north. It would change the growing seasons, some for the better for some plants and some for the worse. All of this is influencing our livelihood and our impact. And you can see here, certain things are uniquely threatened. The amount of melting of snow in the ocean or glaciers and all can have a pretty impact, especially in my area. So, like you say, there's both positive and negative impacts to the greenhouse. But overall, the negative impacts are winning out, unfortunately. And here you can actually see the anomalies we've had in temperatures. Really, the land and the ocean has taken off here, combined since the 1970s. So we've been measuring the radiation that leaves the Earth as well. We have satellites up there that do that. That's a way of monitoring the climate. And some of these satellites have definitely shown that the infrared radiation that normally would be leaving the Earth isn't leaving as much. So this is all that area. I just wanted to show you quickly how we can use these radiation in different wavelengths. So, for example, here's visible. If we were up on top of the Earth looking down from space, that's what we would see. And right here we have lightning superimposed on it. So that lightning really pushes across here as some thunderstorms. If I wanted to look at different wavelengths, we've actually got red, green, blue kind of here all together, looking at different wavelengths that lean towards them. Then we have, you can see snow and ice, cirrus clouds are this wavelength. Water vapor is this wavelength in the middle of the upper atmosphere, but it's a different wavelength than lower atmospheres. So all of that shows the different aspects of how we use the information we got from the atmosphere to help our weather forecast. So hope you got a little bit out of this, and let me know if you have any questions.